So now we're going to move away from objects that are actually in the process of rotating, and we're going to use what we know about Newton's second law in linear world and rotational world to apply it to objects that aren't moving. So it actually turns out that in a lot of ways this is going to be easier because we're not actually going to have to calculate the moment of inertia of the objects, because the right-hand side, the I alpha term for rotation in Newton's second law, is always zero. Same goes for the MA term. So what we have here is for static equilibrium that we're going to have both the sum of torques equals zero and the sum of all forces equals zero. So you're going to set up these two equations in order to solve for various things. So both sum of torques equals zero and sum of forces equals zero means that there's no any acceleration of the system. There's no linear acceleration of the system. So the acceleration of the center of mass, right? The tangential acceleration of the center of mass is zero. Oops, I put that under the wrong one. So the acceleration of the center of mass of the system is zero, and the angular acceleration is zero because there's no torques acting either. So in order to analyze an object, let's think about when these might or might not be true. So for example, let's say that I have an object here, an extended rod, and it's just like sitting on a frictionless surface. And then two people come up and they are going to push on it. Let's say that one person pushes over here with some force F, another person pushes over there with another force F. Well, what would happen to that rod if that happened? Well, it would rotate. Its center of mass might not move, right? Would not move because the sum of forces is zero, but the sum of torques is not equal to zero. So that means that this is not in static equilibrium. And so you can have a situation where there's no net force, but there is a net torque, for example. So instead, what you would have to have, is something where you have no net torque and no net force. So for example, let's take the same long bar. Let me go ahead and apply my two forces to the top here. Well, that's not going to make the rod rotate, but it would make it move, right? It would make it move and have a net force in the downward direction. So then if the center here, I actually have something that is twice that, then what's going to happen now is if we look at the sum of torques and we look at the sum of forces, then in this case, we're going to have the sum of forces is equal to zero and the sum of torques is also equal to zero. So this is static equilibrium. All right, so different examples, a lot of it, you just imagine maybe putting the object there and just thinking, what would that object do? And one interesting thing that's going to come up then when we do these problem solving with static equilibrium is that we're actually going to be able to figure out forces that are acting at the hinge of a beam, or at the surface between, say, a ladder resting up against the wall and the friction with the ground, right? So things that maybe don't show up in our torque equations but will show up otherwise. So when we analyze our static equilibrium problems, what you're gonna do is, generally, it can't hurt, just always do sum of torques first. That's my advice. Just always start with the sum of torques equals zero first before you worry about the forces. And the reason is that forces are forces. Forces, if it's acting on an object, then you have to include it. But for torques, then because some of those forces could act where you choose your pivot, then you can ignore them. So you're actually going to have less unknowns in your torque equation if you start with torque. So always start with the sum of torques equals zero first. So what you would do is you would choose your pivot point so that you would have some unknown forces there. So choose a pivot point where you have unknown forces so that their torques are 0. Now, let me show you an example of what I mean by that. Let's say that we have this sort of kind of crazy situation. Let's say that I have a long bar over here, and then at the end of it, I'm going to attach, say, a disc to it. And then at the center of the disc, this whole thing is sort of horizontal in a field here, or sorry, say in a gravitational field. Then I'm going to attach a rope to a ceiling and kind of hold this whole thing up. Well, if you think about this, there has to be some sort of force over at the wall over here on the left, right? Or else this whole thing wouldn't stay up. So what we're going to do then is that you would choose this as your pivot point for the problem, and then every torque that you write down has to be relative to that pivot. So make sure every torque is relative to that same pivot. So when you do torque is equal to R cross F, remember that R points from the pivot to where the force is applied. So it is specific to a pivot. So it's not just the sum of some sort of random torques for random pivots that add to 0. It's the sum of torques around any fixed point. And so if you choose a point where you don't know some information, for example, the force is acting at that wall, then it's that R vector has to be relative to that pivot. So this points from the pivot to where the force is applied. So let's go now to this example that I kind of drew out. So if we go back to this, and I'm going to draw then this extended free body diagram, which is what we do when we do a sum of torques, Newton's second law problem in rotation, an extended free body diagram where I care about not only what the forces are, but where they act. So this is my situation here. This is my pivot. I want to clearly label my pivot. And what I can do then is think about all of these. Now let's just assume I didn't have the full problem statement, but let's assume these are all uniform objects. So the rod would have its center of mass in the center, and so it would have then a downward force that of its own weight. So the mass of the rod times G acting at the center, and the R for that would be equal to L over 2, right? And those are going to be perpendicular in this particular case. So you would do R cross F. And then let's say over here, the disk, its center of mass is at its center as well. So then let's say it has some mass of the disk times G, that's its force, acting downwards. So what are you going to assume then is the torque? For that torque, you would have to use the R that points from the pivot to where the force is applied. So then in that case, this was going to be L plus, and then let's just say that that's the radius. So that would be L plus some radius R of the disk, right? So you're going to have to be very careful when you do your sum of torques for some of these problems to always make sure to take it towards, relative to the pivot. And then this whole thing was being held up by a rope. So there was a tension force that acted that way. Well, that also acts at the center of the disk. So this one here would also use the same R as the weight there, where you would use L plus R for your R cross F term. So then you have to think about the directions of things. So what we would have here is, let's just call our torques that are acting, if I do R across F, into the page negative, and the torques that are acting out of the page positive. Then what I can say here is my torque for my tension, R across F, is positive. So I would have here, R across F would be L plus R for my tension times my tension. And then I'd have to be given some angle in this problem in order to solve it. So let's assume that I was given some angle here. I want the component of the tension that is perpendicular to my lever arm. So I'm going to, in this case, choose the sine of beta. So I have my R across F for my torque. So my torque from that individual tension relative to my pivot. And then I have my downward torques from these other terms. So for example, for the mass of the rod, well, you can notice that those are perpendicular. It's already perpendicular to the rod because the rod is vertical, it's horizontal in this vertical gravitational field. So then I'm going to have minus L over 2 mRg. And then for good measure, I'll put in the sine of 90 so we know where that came from. And then I'm going to have the other into the page torque, which is going to be from the mass of the disk. So minus L plus R, because that's its distance from the pivot to where the force is applied, and then times the mass of the disk times G, and again, good measure, sine of 90. And then I can go ahead and set that entire thing equal to 0. And that's going to be then an equation that I can use. If you actually look at this, I could use that to solve very often for an unknown tension or an unknown normal force. A lot of times this equation will have just a single unknown force. So I could get my tension from that equation. So that's an example of how you might apply this idea of your sum of torques. Key things, again, to be careful about: making sure that every torque is relative to the same pivot, and then choosing a pivot point where there are unknown forces acting. In this case, there are forces at the wall, and we were able to ignore them in our sum of torques equations. All right, and so then once you do that, then you do the sum of forces equals 0 next, but you have to divide it up into sum of forces in the x direction equals 0 and the sum of forces in the y direction equals 0. Now, very often what I like to do is that you can redraw your extended free body diagram as like a regular free body diagram. Redraw the free body diagram to a point mass, right? Because it's just the center of mass that the forces act on. So for this example of this rod here, if I just sort of imagine that's my object, that's the whole thing, right? What forces act on this? Well, let's draw the ones that also applied torques relative to our pivot. So the ones we know about first. First, we have the mass of the rod times G. We also have the mass of the disk times G. And see how I don't care where they're applied anymore. This goes all the way back to the very beginning. We don't care where they're applied if they are just doing sum of forces. That's just what forces do you have? And then I also had a tension force that was up at an angle. Now, if I look at this, that's not an equilibrium because this whole thing is gonna move to the right, but it's not moving. So that right away tells you that you have some forces acting other than these three. And then what you can do is you can add in the forces at the pivot. So that's going to be a key idea here is that you need to add in the forces at the pivot. So what that's going to look like in this case, first of all, sometimes you can guess at the direction. In this case, I know there has to be a force at the pivot in the x direction that's acting to the left, or else this whole thing is going to move to the right. The other thing that you can do is kind of conceptualize to kind of get a feel for that. Imagine you're the pivot. So if you are literally holding onto this rod that's being pulled, you'd be pulling back on it, right? So you could imagine these pivot forces pretty well by actually holding on or imagining that you're holding on at that pivot point. You would then be able to kind of conceptualize these better. So there's definitely a pivot force to the left. Now, there might or might not be one up. We don't know. It kind of depends on the angles and the tensions, but always assume there is. Always assume there is one. If you solve it out and it comes to 0, then you'll have shown that there's not. And if you can't really tell the direction, for example, here we don't really know the up versus the down forces, which way would the Y force act at the pivot, then just guess. Generally just guess up, and then if you get a negative answer, then you guessed wrong. So I would also here draw an F sub Y at the pivot. And then what you're going to do is you're going to just have your axes. Do not tilt your axes. We're not going to tilt our axes when we do our sum of forces or anything. We're just doing our good old sum of forces in X and Y. And our acceleration is 0. So we would write out the sum of forces in X. And we only have 2 here. Remember, this angle is theta. So I could write this as T cosine theta minus F sub X at the pivot would equal 0. And so then I could solve for the force at the pivot because I found the tension with my torque equation. Then I can do my sum of forces in the Y direction. And so I would have here F sub Y at the pivot plus T sine theta. And again, I know T because I did my torque equation, minus MRG minus MDG equals 0. And so I would then be able to solve for Fy pivot. So a lot of times you'll do the sum of forces to solve for those forces, the hidden forces acting at the pivot of some static equilibrium system. All right, so let me know if you have any questions.